Hello, this is Ron Wade, Principal System Engineer in the Timing Products Division of Renaissance Electronics. I thank you for tuning into this series. In this part of our PCI reference clock jitter series, we are looking at independent reference clock architectures. After this little section, you'll have a clear understanding of what is and is not an independent reference clock architecture. So if we look at our detailed diagram of a single lane in PCI Express, the host on the left, endpoint card on the right, we can see in the red boxes we have a reference clock for the receiver on the host and the transmitter on the endpoint, and then the reference clock for the transmitter PLL on the host and the receiver on the endpoint. The definition of PCI Express is that these two clocks in the red box are sourced from separate PLLs, separate reference clocks. That is the definition of independent reference clock. Within that, there are two subtypes. Within IR, there are two subtypes. There's separate reference independent spread, sometimes called SRNS or SRIS, and separate reference no spread, SRNS. SRIS, as the name implies, is when one side or both is generating spread spectrum clocking. That adds a lot of complexity to the data recovery, and we'll talk about that in future sections. One thing I'd like to mention here is that it is possible for the host board to have its receiver reference clock and its transmitter reference clock coming from a single device. The definition is that the clocking for the opposite ends of the data link is separate, not within the same device. We'll talk about that on the next couple of slides as well. So using the IR architecture, we would have a reference clock 1 driving the host board and a reference clock 2 driving the endpoint. And this fulfills the definition of independent reference clock, even though it will be driving the TX and RX PLLs over here. The definition is the clocking across this link, not within the device, as I mentioned earlier. So the other thing about IR architecture that's important to note is that reference clock jitter limits are not specified for IR clocking. So let's look at a by 4 example to gain a little more insight. So here we have reference clock 1 clocking the host and reference clock 2 clocking the endpoint. So we can see that each end of the data link is clocked independently of the other one. And we do note that it is okay for the TX PLL and the RX PLL on the same device to share a common reference clock. We need the separate transmitter PLL here because there is no common frequency source, and so this receiver PLL in blue. The receiver PLL will be recovering the frequency information, which is common for this data link over here, and then providing that to the phase interpolator so that they can find the phase of each of the data streams. So this is one of the benefits of the lane expansion characteristics of PCI Express. And then the transmitter is less critical in that all of the transmit channels easily share it. And then what I said about the host also applies to the endpoint. Now let's look at some examples of IR clocking. So similar to the common clock, in this case what we have is these drawings set up for independent reference clock where the transmitter PLL and the receiver PLL have different clocks. So we have a TX reference clock over here and an RX reference clock over here. And then in this SoC, the TX reference clock is embedded and we have a separate RX clock outside. Now the thing that tricks people a lot is here I've got a reference clock for the transmitter, and then I follow it up with a ZDB to the receiver. This is an IR clocked architecture. The way you can tell is if you start at the clocking input of the receiver and you trace your way back through the circuits to the transmit reference clock, If you encounter a PLL along the way, you're independently reference clocked. And the ZDB here is an example of a PLL. So this is IR clocked. As we saw in the common clock section, if this is a fan out buffer, that does not violate the common clock rules. And then even if the transmit clock is embedded inside the SoC, and I put a ZDB out here, the same thing. This RX PLL is receiving its clock from a different PLL than the transmit PLL. And that is the definition of independent reference clock. So let's look at a little more complex example. So here, the reference clock generators in the diagram are these little green boxes with the black borders. I've spread them on each of the devices. It could be a discrete small clock generator, but it could also be embedded in each of the devices. It doesn't really matter from a PCIe architecture standpoint. And then up here, I've actually shared the reference clock between these two CPU PCIe hosts and these two. So we can look at the data channels, and the data channels are clocked from separate devices here. And so this is independently reference clocked. The great news for IR clocking is that the clock routing is much simpler because you don't have to get a single clock source around to every device. The downside is there's no specified jitter limit, so you can't easily determine your compliance to the PCI SIG specifications. And these may be integrated in the specific devices so that there would be fewer discrete components on the board. So again, this is all independent reference clocked on these PCIe segments or lanes in yellow. So that concludes the presentation on independent reference clocked architecture. Stay tuned for additional presentations in this series, and thank you for watching.